Welcome to another episode of the Insight Stream, Science Meets Philosophy. I'm Ryan, and I'm honored to guide you through this thought-provoking series brought to you by the Bhaktivedanta Institute, located in Gainesville, Florida. This podcast explores the profound connections between science and philosophy, two disciplines that, when combined, offer deeper insights into the nature of reality and human existence. In this episode, we explore a consciousness-based approach to fundamental physics and cosmology. Our distinguished guest is Dr. Doug Watson, a theoretical physicist from Vanderbilt University. Dr. Watson seeks a theoretical framework for integrating consciousness into fundamental physics and cosmology. He was a National Science Foundation postdoctoral fellow at the University of Chicago and currently serves as a consultant to the Bhaktivedanta Institute, an international consortium of researchers exploring the frontiers of science and consciousness. This conversation promises to be a captivating journey, bridging empirical science with timeless philosophical inquiry. Thank you for joining us as we explore these fascinating ideas. Welcome to the Insight Stream. Yeah, okay, so it's great to talk with you because for a number of years now, I've been kind of at the periphery of what you've been doing, and I am quite nosy. I like to know what's going on, but I don't really know exactly what you're doing. I've got your bio. What we've got, like cosmogony, cosmology, cosmography, maybe. There are so many cosmos. What are they? Like, and which one do you do? Which one are you interested in?
Yeah, that's a great question because you hear these words thrown around a lot, like astronomy, astrophysics, cosmology, cosmogony. What are all these things? And I would say generally, um, these might not be the strict definitions, but cosmology is kind of like just thinking about the whole universe, how it's evolved, where it started from. Technically, cosmogony. Um, I think would more represent like the start of the universe, if there was a start.
Hmm.
And astronomy is more like the mapping of the sky, like the cartography, like the map behind you, how we can map the sky.
Oh, I see. Okay.
And astrophysics is more like how do the objects in the universe, how are they governed, like stars and certain things, how are they formed? Much more related to particular things. And
Hmm.
cosmology is like the whole big thing. So for me, I was kind of interested in everything except for the astronomy part. I wasn't so interested in like how things get mapped out or anything.
Hmm.
I just wanted to know why were things doing what they're doing? Like
Yeah.
why is it this universe? Why does it look like this? Why is it evolving like this? Where did it come from? And that was just an itch I had to scratch from a young age.
Hmm.
Um, and that's gone in a lot of different directions. Obviously, now, including the idea of consciousness is very far from, say, like what I did as a graduate student or something. And I'm sure we'll get to that.
Hmm.
But I think in general, if you just have in the back of your mind that cosmology is kind of the study of everything with the universe.
Like you said, why this universe? I'm curious what you meant by that. Like, what was it that got your attention?
Over cosmic time, basically as the universe grows, more and more structures start to form, like galaxies and planets and
Okay.
stars. And to model that, you kind of have to figure out how to make almost like a scaffolding for this to happen. How are they going to clump together? What will be their distribution? All of these sorts of things. And the complicated thing is you can do that to a first degree, but then if you think about our sun or something like this, an astrophysical object or a galaxy, these things incorporate chemistry, hydrodynamics, regular physics, thermodynamics. They're very, very complicated.
Hmm.
Um, so you basically have to make a lot of approximations. But in cosmology, what you're concerned with is the big scale. You don't have to get everything right on the small scale. You just want to get the general flavor of the universe as it evolves.
Okay.
So we would develop simulations, and there's so many. I mean, with space telescopes, James Webb telescopes that are just mapping all of these objects in the universe. You basically run your simulation and see from your starting principles if it actually looks like that in the end. And
Hmm.
some of these are remarkably successful. It's quite amazing. None that I did, but
Well, you get sometimes the luck of the draw, though, isn't it? You're in a certain project, and yeah. Uh, on this topic of simulations, um, so when you say run a simulation, what does that mean? Like, what are you doing? Are you just so you've got the say the Webb telescope, whatever, and you've got these facts that are coming, like they're reporting facts. Is a simulation something on a computer that you run and you just want to see if it verifies those facts that are coming in from a telescope, or what does it mean?
yeah, so what happens is what astronomy and cosmology is fundamentally based on is the fact that the speed of light has one speed. It's a fundamental speed. It's constant. Einstein told us that. And so it takes a certain time, like I was saying, for the sun, for a, a photon of light to reach us. So really all telescopes do is grab photons from distant objects.
Hmm.
And the longer it takes for one to get here, the farther away it is, meaning you're looking farther back in time. So we have telescopes that do all sorts of different things that extend our senses. So some image the universe in X-rays, some in microwaves, some in visible light, and some go deeper than others, while some concentrate on just getting the minute details of things that are close by. So what James Webb does and other telescopes is they look at basically slices in the age of the universe. So going farther and farther back in time, let's take a galaxy, for example. What do galaxies look like, very close to the start of the universe? What do they
Hmm.
look like a little more recently? What do they look like now? How have they changed? So there's an evolution to how structure forms in the universe. And what we try and simulate, it requires these massive supercomputers, is basically build a bunch of galaxies that we think is how they start out. And then we
Okay.
just run them forward in time under different physical assumptions like gravity or this or that. And in the end, you get a distribution, a statistical distribution of objects. And then you see if that matches the observational data to any real degree.
Hmm.
Um, so in that way, cosmology has been very successful at doing that. On the other hand, you might have heard of some pesky little things called dark matter and dark energy.
Oh yeah.
Yeah, yeah. Let's get into the weird stuff. Things, are very, very influential in how the universe evolves. Dark matter is what we think, we really don't know, is some sort of particle that doesn't interact with light, but only interacts with things gravitationally. And we think there's a lot of it. So that will change how galaxies form and big structures in the
Hmm.
universe. Dark energy is also mysterious. It's the vast majority of say the energy budget in the universe. And it's what's causing the universe to not just expand, but that expansion to accelerate.
I
So
see.
this is what we call the dark sector of the universe. And we're quite clueless on what is happening here.
You're in the dark, basically.
Way in the dark.
Hmm.
So you can model its behavior, but what it is or what they are, no one knows. And it's been like this for about 30 years, if
Hmm.
not longer.
I thought I heard something recently, and don't know where, that there's been a bit of a turnaround, and I suppose it's complicated in academia. There's different people saying different things until you build a consensus. That kind of perhaps these are um, not the best. How do you say? Postulate. Is that word postulates? Like when you postulate something, and because we don't know if it exists, but we're just trying to fill a
Yeah.
space. Have
Yeah.
you heard anything about that, or are they still kind of, dark energy, dark matter, still the kind of go-to
I mean,
ideas?
I think if you if you went to a conference and polled the audience, I would still say a large majority think that there's something like dark matter and something like dark energy,
Okay.
just because of how well this seems to match the data. On the other hand, the the equations we use to model the evolution of the universe are actually pretty simple, believe it or not.
Hmm.
But it's been very successful. The problem is it hasn't given us any insight into what these things are. I could go into detail about it, but I think it would lead us too far astray. The point that I wanted to make is that what's hard for me is that on the one hand, there's the academic literature that you read and you learn about new ideas and this and that.
Yeah.
And then what's around much more now than when I was a postdoc or anything like that is the ability to just throw out ideas on YouTube, for example.
Hmm.
Seems very, very definite. Like they've found this new thing, click on
Right.
it, learn about it. Um, but in reality, I think the state of things are more like there are some fundamental problems that haven't been solved, and it's been a long time. So that should mean, yeah, we should be thinking about potentially other theories, but those other theories have to be just as strong at reproducing the data.
Hmm.
And what we can get into, if you like, which is my favorite subject, is the very early universe. So that sets the initial conditions for how everything will happen.
Okay.
That's the most complicated part in this story for sure.
So you're because it's so like you're describing uh the evolution almost of the universe, at least in terms of how it seems to manifest, can be kind of modeled. But where does it come from? Well, we have to look at the early universe because it's coming out of earliness.
Yeah.
Yeah, I'd love to hear about that.
Yeah. So if just like a little short background, um, it's been over 100 years since Edwin Hubble made these observations. So in the 1920s, basically our own galaxy was the universe. And because we hadn't seen anything beyond it.
Oh,
Telescopes
okay.
hadn't advanced that far. What we had seen were these sort of fuzzy little things around it. And, we thought these were certain kinds of gas clouds or something. It wasn't quite clear. But Edwin Hubble at this observatory in California, he measured the speeds of these. You can do this in a particular way where you measure the light and you can tell the direction these galaxies or sorry, these objects are moving. And what he found was that A, they were way farther away than we thought, and
Hmm.
B, all moving radially away from us at the same speed. So imagine that front page news, like
Wow.
there are more than one galaxy, and they're all rushing away from us.
At
So
least
that,
squeeze two nature papers out of that, or whatever
yeah,
the.
for sure. Um, so that started to change the picture. If everything was rushing away, the logical conclusion is that they started from some initial point or whatever it was,
Mhm.
um, so people started proposing ideas about what would later become the Big Bang. In fact, the Big Bang was a bit of a pejorative. Um, there was this Archbishop, George Lemaitre, who came up with this model about how the universe started from sort of an infinitesimally hot, dense state and then rapidly expanded outward. And all the colleagues called it the Big Bang as kind of like jokingly.
Oh, okay.
And now it's still 100 years later, the standard model that we use. The Big Bang is the standard model.
Well, it's not. They're not joking anymore when they say Big Bang.
Not joking, not
Okay.
joking, but there comes some paradoxes with this. For example, what does that mean to be sort of packed down infinitely, and what will cause it to expand? And at the same time, Let me know if any of this is unclear, but at the same time in the
Mhm.
1920s is when the quantum revolution started, when we first started writing down a theory for quantum mechanics. So quantum mechanics is the very, very smallest scales we probe in physics,
Mhm.
and general relativity, Einstein's theory of gravity, are the largest scales. So this was basically all we really were doing was gravity, but now all of a sudden at the smallest scales, there's this super weird physics going on.
Mhm.
It was very strange philosophically. What did all of this quantum mechanics? Everyone knows that there's this weirdness with quantum mechanics. Why does this matter? So if the universe really did start from a very infinitesimally small size, well, that means it's in the sort of quantum regime where all the weirdness is happening. And that's where gravity breaks down. And both of these two, um, well-tested theories. So general relativity, we use daily with everything from GPS to cell phones and mapping the universe. And quantum mechanics is everything that goes into making those cell phones and our computers. So these two theories are just wildly predictive. They're amazing,
Mhm.
but they kind of hate each other, once they start to meet at a certain range. And that
Mhm.
range is what we think is where the start of the universe was. It was that competing battle.
I see.
So, what the heck was happening there? How did any of this happen? The story gets even more complicated because we can't probe the early universe. We're here now. We weren't there billions of years ago to test this. So, and there's also a limit to how far back you can see the universe in terms of light.
Mhm.
So, what we do is we build these giant particle accelerators like the one in Switzerland.
Yeah, just around the corner from me.
Yeah, right by you. And you
Mhm.
smash particles together as hard as you can. And this is said to sort of mimic what was going on in the very early universe, where it was very hot and dense and particles were crashing into. So there you go. You have to assume that laboratory physics is the same conditions that were at the early universe.
Mhm.
It's a lot of speculation. It's very tough to know what's going on. But that's why it's fun. That's the sweet spot.
Yeah, that's actually that topic of the large hadron or hadron collider. And I didn't realize that's what they're doing, like mimicking early conditions. I really liked your. I'm just going to bring a few things together and just love to hear your thoughts on it. A little bit of a tangent, but anyway. So as you were talking, I was hearing about these two mighty forces that have their own realms, like almost kind of like the deistic vision of the universe of these two eternal forces that are always uh, at odds with each other or whatever. And then, but there was a time when they were held by a something, and uh, and I was just thinking about that, bringing up the kind of mythological aspects, if you like. And it got me considering, like, the Large Hadron Collider. I've heard that one person told me that there's a big statue of Shiva there outside the Hadron Collider. Um, and I'm just interested in that because I know maybe it's to do with destruction. I've got to, so that's one point. I'm just curious if you have any thoughts. But my second question is, isn't it like really dangerous? It sounds like it's play, it's fun, but if we're recreating conditions that formed a universe potentially, isn't that like could it go badly wrong?
Um, it can't, fortunately. Um, yeah, so originally there were some warnings that, hey, if we get to these really high energies and we're crashing things together, you could form something like a black hole from this experiment and then, absorb the whole Earth. Um, Not wild claims. They needed to be shown that it wasn't possible.
Okay.
So no, we're talking about very, very few actual particle interactions. It's not like, so in the early universe, we're talking about an incredibly small scale where all of matter today was in that size.
Mm.
If you even imagine the scales I just talked about with the cosmos, all of that energy and matter was in that infinitesimally small pocket. So no, we can't reproduce that, thankfully.
Phew, okay, great. Because it's close to me. That's what I'm saying. Like maybe you're okay. You're over in America, but I don't want to get sucked up. I've got a
We'll
weekend
start
to.
calling it the Hadron Collider. Is that how British people pronounce it? The Large
I
Hadron?
don't know. I realized when I said it, I've never said it out loud. Um, is it hadron?
I don't know. I guess that's just how, on the
Now,
other side of the pond we say it.
now I'm causing existential doubts.
I'm saying Hadron. As for the Shiva part, that's kind of a cool question. I had no idea that was there. Um, it's interesting because on the one hand, there's some, I guess you could call it destruction of particles crashing into each other. But kind of the beautiful thing about that is particles crashing into each other, how it works in particle physics is that creates new particles. So there may be some
Oh,
sort of destruction where the particles or the entities that you started with are no longer there, but that's because they've transformed into new particles. So it's creation, destruction, creation, destruction.
I see.
It's called actually annihilation and creation. It's pretty cool.
Hmm.
But I did want to mention now because you talked about that expensive map behind your head.
Yes.
And
Thank you for acknowledging it. It's now it's
yeah,
paid for itself.
looks very posh. I like it. Maybe we could use that as an analogy so I can try and help explain this early universe thing a little better instead of being so abstract.
Yes, please.
So if you take a two-dimensional map like the one you have, on so general relativity, our theory of gravity on the biggest scales, tells us that space and time are like a fabric, like a stretchy fabric almost. And heavy objects bend that space and time. All these really weird effects happen with time stretching and length contracting, all of which has been very extensively experimentally verified.
Mhm.
But it's like a smooth fabric, essentially, that can be malleable. Okay. And then on small scales and the quantum scale, and again, sizes we can't even fathom, they're so small. Things are discrete. They're not smooth. They come in packets. So it's
Okay.
like energy comes in packets. All particles are packets, and all of that's how quantum mechanics is described. So imagine taking your map, which has the distances to things and objects and places. We can think of those as like galaxies or whatever.
Mhm.
And imagine starting to crumple that thing up. We're squeezing your map down, your 2D map.
Mm.
As you start to squeeze it and compress it more and more, these distances and other things become more and more unintelligible. They start to not make sense anymore because you're
Yes.
pressing it down so far that what you started with is no longer there. There aren't distances between North and South America or this or that. You've gone to a regime where that's kind of wiped out. So what are you left with? Um, Confusion, I guess, but that I guess that's kind of an analogy where you lose the sense of, distance and time and space. Did that make it
That's
work, or did that make
no, that's it. I'm seeing the little scrumpled map. I mean, I'm feeling a little bit, upset about that, given the expense, but it's crumpled up fine. It's for the love of science. Let's keep going. We've got a crumpled little map, and that is that. Are you saying that's like that would be the kind of quantum realm? It's just kind of not clear where distance is not. It's
Yeah.
obvious. Like,
Well, the quantum theory is a probabilistic theory where we don't really know if you know the position of something, you don't know its momentum. You've heard about all these weird sorts of
mhm,
things. The gravity theory on large scales from Einstein is a deterministic theory. You know the stuff, you know how it's going to evolve, no problem. And things are smooth. So if you wanted a complete theory of the universe, You either need something much bigger than these two that describes everything, or how are you going to merge them? It's a very tricky thing to think about. Um, how do you take something that's smooth and weak and then merge it with something that's very wacky and
Hmm.
realistic? It's a very, very hard problem, and we've made very, very little progress in it over the years.
It's just
Um,
trying to reconcile. There's this kind of desire for harmony to bring it together, these two sides.
well, there's that, but it's also that um, it's just that they both work so well. What when does one transition into the other? If
Hmm.
one works so well, does it all of a sudden become smooth at some scale, and why? And vice versa. So they just don't work together, which, you don't have to lose sleep over. Uh, but it's like sort of it'll be the next sort of revolution in science because something different is going to come out that will look like general relativity on large scales and look like quantum mechanics, but it will be a totally different framework.
Hmm. Is
And
this Doug, is this where we need to advertise like the this podcast is um physicist finds the answer to, and then we just like we need to stop it here before you give
yeah,
the
yeah. Oh,
answer to the
time. Sorry. Yeah. Um,
But do you have any, what's is this something that you're pursuing? Is this because I know you work on um we haven't mentioned the C word yet, consciousness, like that. And I'm wondering if maybe do we bring it in here? Where should we bring that in?
yeah, let's do it here. I think it's a fascinating story, both in science and just where things are in the current realm of uh, the trajectory of science. So, I was talking about quantum mechanics in the 20s, and you may have heard of what's called the measurement problem. There's this very strange phenomenon where things are uncertain, positions, momenta, etc., until a measurement is taken.
Mhm.
And then you can get a definite location or a definite momentum. But what does a measurement mean? It seems like no matter how you do it, that an observer has to interact with that system.
Okay.
That was the initial, what's called the Copenhagen interpretation. There is a whole universe of interpretations now. Um, but in my mind, it seems strange to have a theory that somehow ignores subjective experience within it.
Yeah.
That's a tall task, but we're observing this thing that we all seem to have a coherent story about outside of us that a lot of us take to be real. And we seem to be interacting with it in kind of a mutual participatory way. Um, so is that the missing piece, perhaps? So what's been happening lately in physics, I'll try and think of an analogy on the spot, but this is going to be hard, is that instead of trying to mash quantum mechanics and general relativity together, our two best theories, people are starting to consider could there be something more fundamental than these two physical theories that gives rise to them such that they, to our subjective experience, appear a certain way at small scales and appear a certain way at larger scales. So
Okay.
some
Like a
theories,
common denominator, some kind of thing that
yeah,
underlies both.
yeah, exactly. And people have thought about this a long time. Like um, the theories were so successful that and you could build and make so many things, and we've had so much technological progress. And there's not a lot of money and funding for thinking about these kinds of things.
Right.
But I think deep down, people just thought, there's a layer below this that things are arising from. And there have been some really, really cool advancements in the last 10 years or so for example, you can come up with these beautiful, like kind of abstract geometric structures. This is kind of Platonic thinking
Mm.
that if you evolve them, it's quite complicated, but you recover all of these theories just from an underlying sort of geometry or information system, information
Oh,
structure. So it's a layer below that. It is a little bit abstract, but it's very promising that, there's something that is underneath that is where space, time, all these things are emerging from. And
mm.
I really like that. I think that's really cool. That's the area that I've been very interested in is thinking about um, more abstract spaces, how information could come before space and time. But there's the rub is that you run into the same problem is where does that information come from?
Yeah, yeah.
And why would it make a universe? Where do those laws come from? And it seems to me at this moment in time that information can come from consciousness. It seems plausible, at least at first glance, that it's a
Before you
source.
get into consciousness, I mean, I want to, I don't know where you're going, but I want to just ask, and you carry on and just introduce this where you can. I want to know what information is more and more clearly. Please continue. Yeah.
Sure. Yeah, I'm I'm glad and not glad you asked because uh, it's hard to put your finger on. In every different field, there's a different definition of information. So biology has a definition. Obviously, computer science has a definition of ones and zeros. Physics has its own definition. Uh, I think the point is that an information structure is more kind of like it's like a template. It's like a
Mhm.
blueprint. It's got everything you would need. Um, all you just need is the push to evolve it.
I see.
So let's say you have the universe is made of particles and quantum mechanics and does this. All of the information for that is there in the structure. It's just like a cosmic blueprint. And how those relate to each other, how they interact, and all of that um, is where you get physics. That's where that pops out of. It's the
Mhm.
dynamic. But I think of the information structure as the blueprint and the rules. So almost like a chessboard, you've got the rules to the game, you've got the pieces, there are rules for how they can move.
Mm.
Then you play the game.
Okay.
So the question for me was, and it's obviously a bit out of the realm of science, is, where does the game come from? Who made where did the chessboard come from? Where do the rules come from? And I don't have a strong theory for that or anything other than it seems plausible that the source of this information would be something like consciousness, something
Mhm.
like you can see that has intention. And that would allow uh, conscious agents like ourselves to then participate in that game. So that's what I mean by a theory where consciousness is fundamental to space and time emerging. But
Mm.
actually developing a theory like that, that's a very long-term project. And, you're at the boundaries of physics and metaphysics where, how would you publish something like this? Because it's not
Right.
a physics paper, it's sort of a philosophy paper. Um, but it's what I think about all the time.
Mm. And as you were saying it, I was just remembering about like David Chalmers, uh, not just him, but I mean, I'm sure there's many physicists who speak about this, about taking seriously the theory that the universe is like a simulation. Um, and well, of course, if you have a simulation, um, then of course it's like asking the question again, where does the chessboard come from and the rules? Where does the simulation come from? And funny, interesting, you're kind of opening up the idea that okay, so there's uh, consciousness can be the one that injects this, inputs this information, or maybe structure as well. Is that another way of me understanding it? Is the kind of instead of just chaos, there's actual structure and meaning.
Yeah. Um, Sorry, I interrupted you. I was just saying, yeah, it was like an order that's being imposed.
Yes.
Yeah. Um, so yeah, and the model we're working on, which is kind of fun, is that what generally what's thought of as for making a good theory is starting from the simplest axioms you can. And so this model, a cosmological model that induces consciousness, is kind of like, what are the telltale signs of consciousness? Or, what are the simplest things we observe in the universe? And the starting point that we came from was that it seemingly appears that there's a tendency towards more variety or
Mhm.
more complexity. There's kind of this, and in physics, they usually call this something like entropy, but there's kind of a drive towards more variety. So in this kind of model, it's it's relational, like the relations matter, the connections matter, and they push towards more variety. And that's nice because the thing about consciousness is that it experiences, it wants to experience. So if there wasn't increasing variety, it doesn't quite make sense
Mm.
uh, for what we know about consciousness. And at the same time, we also see a lot of harmony and order. So there are these two competing things of where variety, maybe complexity is growing, but on the macro scale, there's a coherence. Uh,
Yeah.
yeah, there's this order happening. So that's basically the most fundamental principles we start with and try and recover um, the known theories of physics from pretty simple principles. And that's just a way to, at first order approximate what it is that um, we think is somewhat representative of consciousness. But your question about the simulation is, I think, very interesting. On the one hand, I don't think about it too much because it's not provable, it's not falsifiable, it's
Mhm.
just conjecture. And you know how these things go. It's we always make the same philosophical arguments in line with what the technology is of the day.
Yes.
So that surely the analogy will change down the road. But it is very interesting, and people do take it very, very seriously. Um, I just happen to not take it very seriously.
Mm. And you're the model that you're talking about that you're working on. Am I right to think based on what you just said that there's you're kind of taking into account the kind of quantum realm of unpredictability, um, and that are you linking that there's that kind of link to the drive of consciousness towards diversity, but on the macro scale that you of let's say gravity, where there's kind of orderliness and harmony, which is also a desire of conscious agents to desire both. Am I right in that correlation? Is that what you're saying?
Yeah, exactly. And how these interactions happen, who knows? But one proposal is that um, if perhaps consciousness is outside of space and time, it's a non-spatio-temporal, it's something else, then maybe those interactions happen at that layer below with this sort of information structure where that's the communication happening. Um, and so we know that there are kind of physical laws that really govern what can happen in this universe.
Mhm.
But there is very, very clearly, well, in my view, some sort of something like free will, very restricted, but there's something there. And in my mind, that interaction, that free will, that intention, that desire is communicated at the layer below. And that sounds kind of far out.
Mm.
In reality, it's not that strange because if um, if consciousness is not a property of the brain, but is fundamentally something else, then there's no problem with that communicating outside of space and time and but influencing space and time.
I see.
So it's still quite rudimentary at this stage, because these aren't things you can really test necessarily, but you want to build a framework or an interpretation that is at least logically sound. It follows logical arguments, and then maybe it will be taken more seriously. So on
Mhm.
the one hand, there are the individuals, um, with their own little minute conscious, these little agents. But then there seems to be something, a more governing agency that really enforces all of these things to some degree, allowing
Mm.
for these minute intentions, um, that are in coherence with the physical laws and then the intention, the unfolding of the universe. But there's an interplay, there's kind of a dance between all of these. And we're finding that if you do that, you can actually give rise to something like quantum mechanics. And with global coherence, you can give rise to something like gravity on big scales, um, at least to a first approximation. So, you know, that's at least telling us, maybe we're going in an okay direction. Um, and we're just going to keep pursuing it, see what it tells us.
Okay. I mean, it sounds like it's really coming along. And this is what you're describing are kind of mathematical models.
It's both. We get a lot of help from people that are in consciousness studies, philosophers of mind, those sort of things, because that's
Mhm.
not my area of expertise at all. Um, but yeah, there's definitely a mathematical framework to it. There, in some sense, there has to be if you're going to give rise to physics. Um, but that's what makes the project inherently fun is that it requires people from different
Yeah.
areas to interact, um, and actually have like a cordial dialogue where we're not shouting over each other. It's really amazing. It's really fortunate position to be in.
It sounds really fun. Yeah, the intersection um, between some really interesting fields and how do they come together? And it sounds like it's kind of like a consciousness informed physics with and the question of where do these constraints come from as well as you were I think discussing there's we play a board game, we play within the board. So have to-
Yeah, because then the next question is where does that, governing consciousness comes from? And that's where I just, turn to my philosophy friend and I don't have to worry about it.
yeah,
It's pretty easy.
you've got them both on quick dial.
Well, I hope this wasn't too confusing. I'm so deep in the weeds that sometimes I forget how to communicate these things, but
Thank you. Personally, I being a layman, it came across really clear. I like the visuals, the analogies that you gave. Yeah, I've learned a lot. I have one more question because I know we're wrapping up. Is there anything uh, that I didn't ask that you would love to answer? Like a question you would ask yourself that you would like to answer?
whoa. That's a great question. Um, one, I guess, if personally, I'd have to say, I personally have to stop and question myself a lot and say, what are my true aims here? Is it to be someone who came up with some new groundbreaking theory, or is it to push the discussion forward and enhance more dialogue?
Hmm.
And I struggle with that because everyone wants to put the little trophy on their mantle and say, see what I did. But when it comes down to it, I really hope that what wins out is the desire to just increase communication between people from all different fields of knowledge
Mhm.
because it's not happening now. It's a listen to me and stay within my framework. And if anything, I just hope what comes out of this is that there's discussion, there's dialogue, and most of all that it comes from a place of humility. Because in the end, what the hell do we know? Not much. So,
Yeah.
just be glad that we can learn some things. And most importantly, the model is based on relationships between physical things, consciousness. So let's do that. Let's build relationships with it and just, foster dialogue with it.
Thank you, Doug. I love that because it's in the very core of your model as well about relationships. Um, so we like you said, we can't get anywhere if we can't hear one another.
Yeah.
Um, but I wouldn't rule out the little trophy. I mean, I'm looking at your shelf. Maybe there's a bit of room there. Definitely, there's a bit of room on your wall, I'm sure, for a picture of you of a trophy. So I'll look forward to for the next podcast.
Thank you so much, Ryan. Great to
Yeah,
see you.
thank you, Doug.